All right, so we're back with our single tank. Remember we did this in a previous video where we modeled our series of tanks with a differential equation, and we solved IVP to plot that up, how our change of heights responded with a change of time and our inlet flow. This time we're going to be using the same problem, but now we have this idea of a first order transfer function, which looks something a little like this. I'll go ahead and write that out. Some input value, I don't know, or I guess some output. We relate that to some input value, and then we have a system gain represented by k, tau, our time constant, multiplied by our Laplace variable s. So this is in the Laplace domain, and then plus 1. So it's this idea of a first order, the most simple of the transfer functions, where we relate a system output to a system input, basically through algebraic expressions. And the reason why this is so helpful is that when you have series or parallel systems, you can use this algebraic expression. Basically, if it's in series, which is what we're doing today, I believe, we'll be multiplying these across, and then if parallel, we add them, which we may or may not do in a future video. So yeah, this is the most simple one. I believe in most fields of engineering, this is mainly used with the idea of time delays in process dynamics, how a system responds to a sort of change. So that's the time constant tau. So obviously a higher time constant means that we would have a slower response. And then with system gain, that represents, well, how much you're gaining at steady state, your ratio of your output and input at steady state, and whether or not you're gaining from that. So yeah, we can just kind of go ahead, start. Hopefully that's enough time for you to read over the problem, but we'll go ahead and start with our most simple tank here. Just, I don't know, some tank. We have an inlet and outlet flow. We had some height of water denoted by h, function of time. Then we had our inlet and outlet flows, so maybe Q in, Q out. Cross-sectional area, area AC, and then area of the hole where it's coming out, purely gravity drained. Is there anything else I'm missing? I think that's it. So again, we are presented this change in volume as a function of time. So change in volume with respect to time, that was equal to, well, for the tank, it's simply our cross-sectional area times our height. So we have our cross-sectional area AC times AC times our height. So again, a height is a function of time. So we do a change of height with change of time. And again, this is determined by the inlet and outlet flows, Q in and Q out. And remember in our previous problem, I'll try to go through this a little quickly. Q out, we determined this was equal to an expression using Bernoulli's equation with we equivalated, I don't know if that's a word. We made it equal to 0 to represent no losses, but essentially it was our cross-sectional area of the hole times our velocity of that hole. So I can go ahead and do that real quick. So for Bernoulli's, hopefully I think it's double L. We had our injection work over density, and we added that to our gravitational constant. So potential energy, the difference between our 2 points, that's the one thing I forgot to label. So I guess we can pick this point as 0.1 and this point as 0.2. And then, so we have difference of pressure and difference of heights, and as well as the difference in velocities. So that's what Bernoulli's is allowing us to do, relating pressure, height, and velocity to our system. And we're going to be using what we know to find eventually this point, the velocity of 0.2, since it is equal to our outlet flow. So for a little bit, Remember we said in our previous problem, and it applies to this one as well, both points are open to atmosphere, so there's no change in pressure here. Keep hitting my mic, sorry. Yeah, there's no change in pressure here. So that's 0. And then remember the difference between 0.2 and 0.1. Well, that's a negative value. If we determine it by h, that would be negative h. So something like negative gh. We determined that the velocities, well, the cross-sectional area of the tank was much bigger than the cross-sectional area of the hole. So we assume that the velocity change of that cross-sectional tank, how it's changing from those heights, is relatively small. So we just say that's 0. Now we're left with our expressions, our velocity and our potential energy. And isolating for velocity, we should have, so gh times 2 and square root. So that's our equation or expression for velocity 2 at point 2, the outlet flow. And then substituting that back in, we have our expression overall. So cross-sectional area of the tank times height, that's our volume change, inlet flow, and then minus our change in our cross-sectional area of the hole times 2gh, which represents our velocity. Pretty much the same thing as conservation of kinetic energy, like dropping a rock, pretty much, where potential energy equated to kinetic. And if we want to, well, the end goal here is to try and relate this somehow to our first order transfer function. And to do that, we have to take a Laplace, or turn our variables into a Laplace domain. But for in trying to do that, we have to know that this h that's actually under a square root, this h to the 1/2 power, is actually nonlinear. And with in trying to take a Laplace of this expression, this differential equation, we actually need to make sure that these are the dependent variables have constants, are constants, and shoot, there's a word I'm forgetting. Yeah, we'll just say constants and have to be linear. So essentially what I mean to say is that we need to linearize this expression. So in doing that, we'll have to approximate this dependent variable doing a Taylor series expansion. So do that, we'll have something like h to the 1/2 is our function, and we're going to approximate that. So that will follow the kind of expression below, where we approximate a function where we do a center of expansion around some arbitrary point. And this point will actually be important later on. For now, we'll do arbitrary points, and then I'll show you a wrong way to, well, not a wrong way, but a significantly harder way to do it, which we won't follow through, but then we'll do it in, essentially we'll have a center of expansion that is at the steady state value, and doing so will allow us to evaluate our differential equation much easier, relate it much, in a way that's much easier, I should say, to our first order transfer function. So when we have our Taylor series expansion, we do it about a certain point, so x0 maybe, and then we add to that initial value the slope, so the derivative of our function at that point, which we know, and then that how far we change from our initial center point of expansion. So we'll do something similar. Well, I guess I'll just draw this out. So if our function is h to the 1/2, so that's a root power, so it looks something like that, where it's kind of growing slowly, but it doesn't really, the slope doesn't end up becoming 0. And then say we have some points, so maybe here we have h, so I'll just use h of x maybe. Does that make sense? Maybe I'll do just h, I don't know, h, and then, well, I don't know the best way to express this. Maybe we will use h of x. Okay, and then we'll have another point, which we do know, our center point of expansion. So maybe x naught. And then we have our x-axis values. So this will be x naught and x. I guess it might have been better to use the actual example. So let's use it in terms of f of x. We know we're trying to find this f of x, which we're approximating from a center point of expansion, x naught. And this is x naught, and this is x. So we're interested in seeing how far did we change between x and x naught? What is that difference? Well, to do so, we need to obviously have our initial value that we started at. So that's right here. And then to get this change in height, I suppose, or how much we change along our function in blue there, we want to add our slope. So there's a slope here. Hopefully there's some sort of, hopefully that looks like a straight line, but kind of like a tangent about that point. So that's just our slope. That's a derivative of our function. How much did it change at that point? And then we also have to multiply that by how far did we go along the x-axis? So the width of this between the two spots here. So that would be x minus x naught. So I guess kind of denoting colors, this is our width, and then this was our slope. Oops. And then of course our center point of expansion at x naught. So again, we rewrite that for our root function. We have so h to the 1/2. So we evaluate h to the 1/2 at h naught, something similar, an arbitrary point of expansion for now. So we evaluate it at 1/2. We add to that the derivative. So the derivative of h to the 1/2 is simply we bring down the exponent, so 1/2, and then we subtract 1 from the power. So 1/2 minus 1 is 1/2 minus 1 is negative 1/2. So that'll be a negative square root. So that would be right there. And of course, we have to make sure it's evaluated at our point of expansion, just like how we did down here. So that's why I have evaluated at h naught. There we go. And then subtracted by how far we went along. So that's just simply h, our function. So it could be any point we choose. So that is again, this is h representing our function, the root function, and then subtracted by our original position, h naught. Our point, or I should say our point of expansion. So if we plug all of that in back into our square root of h from our original expression, let's see how well I remember this. I don't really need to remember. I can just go up if I forget. So we have our cross-sectional area of the tank, derivative respect to time of our heights. How that changes with time, that's our change in volume. Our inlet flow, subtracted from our outlet flow, which we represented with Bernoulli's. That was the cross-sectional area of the hole times 2g. And now we expand our cross-sectional, or our root h function. We linearize that since it's a dependent variable. We're trying to get our expression in terms of, well, make it linear. So we did the Taylor series expansion, which was h at the point of expansion to 1/2 plus, and then we evaluate this. So now we can actually evaluate it, meaning I just plug in h naught for our h there in the 1/2 square root h. So that's our derivative of our function. That's our slope. So I plug in h naught here, and then we multiply by how far we traveled, which was h, which is still a dependent variable, but now it's linear, minus how far we went from our point of expansion, which is just the difference between these two. So now we have a very long expression, and you might think, well, now since we linearized our differential equation, well, the whole point of that is so that we can do the Laplace of it and make it easier to solve, and well, eventually simplify it down to our first order transfer function. But well, I'll go ahead and do it here, but I guess we might go in on a side about Laplace transforms. Yeah, you know what, let's do that. So eventually we're going to be doing Laplace transforms of our derivative, our function here, respect to time, and then our, well, this is another function. So those are two different Laplace transforms, and we also have some constants here, which will also need a Laplace transform. So I'll go ahead and do those real quick. Again, you can always look these up if you don't know, but just for my sake to show that I can do it and I know how to do it, I'll do it here so that in the future I won't have to do these anymore, or at least show them so you know where these are coming from. So if we'll start with the more difficult one. We have the Laplace of a function, or our derivative with respect to time. So essentially we put this in the S domain by multiplying, well, of course, our bounds first are from 0 to infinity. Then we have the function that we care about to take the Laplace of. And of course, every time we do a Laplace, we multiply by e to the negative st. This is so we transform it into the S domain. And of course, this is going to be integration by parts. So right now we have the form of, well, we're trying to identify which forms to use. So of course we have to define u and dv. Of course, this derivative kind of matches this existing derivative already in place. So that's why I'll choose that as dv. And then we have u, which is the only remaining one, is the exponential. And of course we do the opposing functions. So we take the derivative of u. So we bring the s down, that's negative s e to negative st. And then integral of dv to get v, well, that's just h, our function. And of course, integration by parts kind of follows the product rule, where we have uv prime is equal to u prime. I guess I should use not the apostrophes, but the d's for the derivative. I don't know, u dv plus v du. And of course, our form right now, we already have it. It's u dv. So if we isolate this, u dv is equal to uv prime minus v du. And of course, do our wiggles for integration. And we do, so uv prime. So this is already the integral of the entire function, which is already, you take the derivative of, so that cancels. You're just left with uv. And uv is h, v is h, and u is e to negative st. And of course, we still evaluate that at 0 to infinity minus, so v du. So v du is h, and du is negative se. So the negative s makes that positive. We bring out the s, and we wiggle this to 0, negative, or infinity. And we still have our v, so v du is negative se. So we're just missing our exponential here. And what you'll notice is that this is actually the Laplace transform of h, which we can also do later on. I'll go ahead and do that after this, but then simplifying this, the left-hand side expression, we have, so we're evaluating this with respect to t. So if e is to negative st, we plug in infinity. Well, that's 1 over infinity pretty much, which approaches 0. So we put a 0 there. And then we have our the bottom bound, so that's 0. And of course, well, I guess this is unspoken, but this h is obviously in terms of time. It's a function of time. So we also evaluate that at 0. So if e to negative st and t is equal to 0, the exponential becomes e to the 0, which is just 1. And then h is thus evaluated at h of 0. And of course, you might be thinking why we chose h infinity over, or why we didn't choose that over the e to negative s infinity. Well, you'd have to do Le Chateliers, which I'll refrain from doing just to keep things simple. But doing so, you'll notice that we take the derivative of the function, and you'll see that with Le Chatelier's principle, the exponential wins, so that eventually it goes to 0 for the left-hand side, if you did evaluate at infinity. So with that being said, we have our final expression that we use is the Laplace of dh dt is simply sh. So that's the Laplace of h as a constant. H as a constant. minus the initial value of h. Also do Laplace of a constant. Why not? So this should apply to, well, actually, it won't apply to these two. These are I'm sorry, these are the actual constants. H is still a function of time. I misspoke there. So if I can move along here. Okay. So we take the Laplace of h as a function of time. Same exact idea. So 0 to infinity, h e to negative st. Now I choose integration by parts again, but now I choose h as u, since integrating this is simply a constant 1. And dv, oh, the only thing left is e to negative st, and you take the integral of that. That's negative 1 over s e to negative st. And so we have that whole business of the product rule. Well, that's what integration by parts essentially is. So we want uv prime and v du. So doing so is uv prime is negative h over s e to the negative st, evaluate 0 to infinity. And then we have uv prime, so v du, so minus v du, so that's a plus with the negative 1 over s, v du, and that's just the integration of a constant. So essentially this, e to negative st, 0 to infinity by dt. So yeah, hopefully there's nothing I'm missing here. Did I do this correctly? I think so. Yeah, this is it. So if we evaluate this, infinity, so again, exponential wins, so we have 0, we subtract, but there's a negative in front, so we add, and then at 0 we have, I don't think I did this correctly. Well, essentially we get, well, I mean, I don't think we have to evaluate this since we always use h to represent it. I'm going to try. I don't know if I'm doing this correctly, but I'll try this, and then if I skip over it, then that's how you know we're not going to talk about it going forward. But let's see. So that's 0, and then we evaluate at 0. So that's 1, and we have negative h over 0 over s, which is a constant. I do that uv prime over v du. And this, do 1 over s. Did I integrate correctly? Yeah. Divide by versus derivative, you bring it down. Yeah, this is right. So 1 over s squared. Integrate. Oh, I don't think this is right. Okay. So we have this, copy down. Negative infinity, or to infinity is 0 minus, and then 0, 1, 1 s squared. Yeah, this does not look right. Yeah, I'll pause to save time here. Yeah. Okay, sorry about that. I think most of my confusion is coming from trying to distinguish from the fact that h of t could be any function. So let's, for simplicity's sake, we'll just denote that as h. Obviously, if we plug in h to the 1/2, we can solve for that. But again, we're just trying to get this in terms of the Laplace domain. We're not actually trying to show with the S domain explicitly. So I'll go ahead and redo this, but in terms of treating h now, we'll just say for now that it is, erase all this. We'll say that it is just h, But now if we were to treat this as a variable, like something like, or a constant, I should say, like h naught, our point of expansion, well, now we can actually do this treating it as a constant. Pretty simple, actually. No need for integration by parts. We just pull it out of the integral, and we evaluate e to negative st dt. Of course, exponentials, I don't know, we can factor it out something like this. We just bring out negative 1 over s, and then this is, of course, again, e to negative st with evaluated as 0 to infinity. So I'll pull these two out. At infinity, and we know that as 0 already, and then we subtract, so evaluate at 0. E to the 0 is 1. Anything to power of 0 is 1. So we put a 1 here, and then you'll notice that the negatives cancel out, and then we're just left with, I should have an equal sign for all of these. So negative 1, this is obviously negative 1, and then you're left with our original variable, or our constant, over s. So that's the Laplace of a constant. It's just the constant over s. Okay. Sorry about that tangent. Just trying to prove something to myself, I guess. So if we take the Laplace of this, which I think I mentioned already, is the wrong way to do it, or at least a more difficult way to do it, you would have something like so constant, that's all right. Laplace of the differential. Well, we did that already. That's just s times the Laplace of h minus the initial variable. So sh, s our Laplace variable, and h at our 0, the initial value. Qn is actually also a dependent variable, but we didn't need to linearize it since it's already linear. So we denote that by doing a capital Q. That'll show up again later. So I'll do a capital Q in. And then the constants, we don't do anything with constant here, though, because these are factors we take out that we multiply in. We could have just taken those out. But essentially, this is, we can do our Laplace inside for this expression for h naught to the 1/2. That is just h naught to the 1/2 over s. We have more constants. And we take the Laplace of these two. So h by itself, remember h is a function of time. We just do Laplace of that would be big H, and then a constant over s. So you'll notice that this is very troublesome equation, since how are we trying to relate this initial value to our Taylor expansion centered around h naught? So that's the difficulty of doing it this way. You could do it this way, but it's preferred not to if we want to try to achieve our original expression up here of our first order transfer function. So doing so, to make things more simple, if there is a way we could relate our initial values to our Taylor expansion, that point, well, this would be a lot easier to simplify. And do that, we actually do something called a deviation variable. So that is, we use h prime, and note this is not a derivative, this is just a notation. To simplify for our deviation variable, h prime is h minus h, and we'll use h bar now to denote the initial steady state. So the deviation variable is, in our case, we're going to be choosing the Taylor series expansion center point at the initial steady state, so that we can relate this h at 0 to, well, not really relate, but we'll get rid of this term of, it'll be h prime of 0, which becomes 0, and then we can somehow get our Taylor series expansion in terms of a center point at initial steady state, and you'll see that here shortly. So first I'll just rewrite it in terms of our center point. So something like, now we say h naught, which was an arbitrary value before, denoted with the, well, h naught here. We're now going to say that it is now equal to h bar. I'm sorry, just h bar, I'm sorry. So h bar as the point of expansion for our initial steady state. And the reason for that is this is for this idea of a deviation variable, which is going to be very important as we simplify our expression. So rewriting, we have copy everything down here from the top here. So this is dh dt. We have qn still. Most of this is just the same. It's just we're changing our Taylor series expansion center point instead of the arbitrary h naught in terms of h bar. So h bar representing our steady state values. So remember, if you remember from when we did the tanks, and pretty much every time we've done solve IVP, we have to use this idea of initial steady state to solve our initial value problem. And that's exactly what we're doing here. So h is still h, but then you'll notice that this h bar, well, that's just h prime. So I'll leave that for now, but you'll see why this gets important, or kind of a recurring expression later on. So now, when we define our Taylor series in terms of our center point at h bar at initial steady state, well, initial steady state value, I should say, now we define our whole expression in terms of at initial steady state. So what I mean by that is now, well, at steady state, our differential is now 0. Obviously, nothing's changing. At least the rate of change is not changing. It's 0. And now we have our initial steady state. So we remember that I use h bar, this bar denoting that is the value at steady state. So now, again, remember this q, we took a Laplace transform, I should say. And that's because it is also a dependent variable with respect to time. So for now, we'll just use q bar. Denote that. Copy down our constants once more, again from Bernoulli's expression with potential and kinetic energy relating to our outlet flow. And then now, again, well, our Taylor series is still pretty much the same. The only difference is that we are now evaluating it instead of h at any h. Now this is at steady state, meaning it is at our initial value of h. So you'll notice that this actually cancels out, since from our Taylor series, if our x is now equal to x naught, well, we haven't moved one bit. It's essentially the same exact point right there. So the change is 0 for that. And now what we want to do is, well, what we'll end up doing is, well, actually we can do that. Well, yeah, we'll do it all here at once. So what we have is we'll subtract our values. So we have our expression of our differential equation with our Taylor series expanded around the center point of h bar, that initial steady state value of height. And we subtract that from our actual initial steady state, where the expression is equal to 0, the differential, I should say. And now we have initial values for all our dependent variables, and subtracting them like so will give you an expression like this. So I'll leave the left-hand side open for now. So we have q in minus q bar in. Then we have our constants again, our outlet flow. You'll see that these initial values actually cancel out. So that's very helpful. If you remember in our expression here, we had no way to get rid of them. Now they just cancel out by themselves. So that's very nice. And then now that, well, this expression is 0, since our point of expansion at initial steady state is, well, itself, we didn't really move. It's 0 essentially. And then we just keep our expression for the slope and our change here. So that is just our slope. Remember the derivative of our function evaluated at, of course, our initial value, and then h minus h bar representing our, again, how far we moved along the x-axis. Now you see these reoccurring, the dependent variable minus their initial steady state, and that's exactly what we want to do also on the left-hand side. And to do that, we can write something in the derivative that's equivalent to what's written above, which is just the exact same thing we're doing here, dependent variable minus steady state, or initial value with respect to time. And the reason I can do that, well, it's because if you remember our deviation variable, h prime is h minus h bar. Well, if I take the derivative of this, it's actually the exact same, since, well, you take the derivative of h, and then this is just a constant, so it goes to 0. So they're actually the exact same. So that's why I can do that. And now, erase that. That out of the way, now we can actually substitute in our deviation variable here. So we'll go ahead and do that. Let's keep it in white. Why not? So cross-sectional area, again, this is volume. Now we're using deviation variable, another deviation variable for the inlet, copy down to constant for this outlet flow, and then we have this height, which was Taylor series expanded, but now it's simplified to just these two expressions. Again, our derivative, and then, well, this is just h prime. Now this is a lot better of a simplification, or to work with algebraically, than what we had right here. So you notice a lot of the variables are gone. We're mostly left with mainly constants. Well, you'll notice this is a constant. So actually, I might go ahead and just label that as, let's do b, like we did in class. So b, and then we can just take the Laplace transform of this. So pretty simple, exactly like we did above. So we have cross-sectional area, then Laplace transform of our derivative, or dh prime over dt, the change in height. Now in terms of the deviation variable, we have, well, sh, remember our Laplace transform we did over here. So sh, so s times Laplace of h minus that initial value. Well, now you'll notice this initial value is actually 0. So that's what I was talking about earlier up here when I was talking about right here, this idea of trying to get rid of that value, since there's really no way we can get rid of it. Well, now we do it right here. Well, remember h prime. Well, what is h prime? Is equal to h minus h bar. Well, h prime at 0 is essentially just saying that this h prime at 0 is the initial value steady state, since remember we're doing this as a deviation variable from our initial values. Essentially, we're doing h bar minus h bar, and that's just 0. So this term becomes 0. That's why we went all out of our way to do that. Again, Laplace transform of q is just big Q. Again, this is now in terms of a deviation variable, so keep that in mind. We simplified those constants to b, and then h prime is just big H. So now we're almost there. Hopefully you kind of see where we're headed towards. H, our height, is the output, so I guess it's worth drawing this out. We have a input, which is our Q in to the system. Oh, that is horrible. Something like that. System. And then we have our output, our height. So we put in some inlet flow rate, and then we get out a height. And then to do that, we have to go through what is called our transfer function. So essentially, we're relating, again, the input to the output of the system. So to do so, we're going to have to isolate h on one side, the output, and the input q in, the inlet flow, on the other side. And that's how we get our first order transfer function right here again. I think that's the third time or second time I talked about that. Okay. So doing some algebra, moving things over, we have cross-sectional area, s Laplace variable, and then we add over bh from the right-hand side, and that's equal to q in. So I just moved this over, this one. And then I'll factor out our h, our heights, so cross-sectional area s plus b equals q in. And then all we have to do is divide across. And now we isolated our variables. But what you'll notice here is that our our expression isn't quite the same. We have a k and a tau s plus 1 in our fraction. So if we want to do that, the best way to get a 1 right here Well, we just need to divide across. Sorry, my voice is raspy. Okay. Excuse me. So we have our height is equal to Qn, and if we divide across by b within the fraction, so it's still equivalent, we have AC over b, and then s plus 1. So now you'll notice that for our same first order transfer function, to get the same expression, we have now related k is equal to 1 over b, tau, time constant, again, k is the same game, tau, the time constant is cross-sectional area over b, and that's of the tank. Then b is what we wrote as our expression relating the outlet flow. So, of course, times our height, which is in the Laplace domain now. So, area of the whole from Bernoulli's to g, and then divided by this derivative from our Taylor series expansion, which is just 2 over h bar. I believe that's right. AH2G over 2h bar. Okay. All right. So I think that's actually part 1. So yeah, part 1. Yeah, we subtracted from initial steady state solution and then did the Laplace. Now for part 2 of this video, we're going to be doing 3 of these gravity drain tanks right here. And it's actually pretty simple, what I mentioned earlier with the this whole idea of this first order transfer function is that when we get it in this type of expression in the Laplace domain with our inputs and outputs, if we want to relate those, it's simply whether if it's in series, like it is for this video in the problem statement, we'll be multiplying those algebraic expressions together. And then parallel, again, may or may not be done in the future. That will be with, we'll be adding those expressions. Okay, so I don't know what makes most sense here. I might just do a simplified version of this drawing just to keep things relatively simple and fast for me. So we'll do something like this. Very rough drawn. So we have flows and we have heights. This is so bad. Okay. Height 1, height 2, and height 3. And of course, Q in, Q1, Q2. Okay. So if you notice, we already have an expression relating height and Q of flow in. So we can just denote that as 1 here. So I'll go ahead and rewrite that maybe down here on the left. So height 1 is equal to Q in times, I'll go ahead and write it out. Why not? So 1 over B, actually, I'll just substitute it in later. So K over tau S plus 1. So now we're interested in getting Q1 somehow. So we have to somehow relate Q1 and H1. So is there a way we've done that before? The answer is yes, because Q1 is simply our new inlet flow, but remember that is the outlet flow from our previous tank. So we relate that using, well, how have we related height and our outlet flow? Well, you'll know that this entire expression originally was just our outlet flow. Remember, we expanded this right all the way from here when we did Bernoulli's, and then we did the Taylor series expansion. That's not it, but so this was Bernoulli's, and then this was the Taylor series expansion. Pretty much this entire thing. So when we simplified it down after subtracting from the initial steady state solution, we got, oh yeah, we just used B, didn't we? So we just used B. So to relate height and the Q out, essentially, this, well, it's the outlet flow, that's the inlet flow for the next tank. So that this outlet, this Q1 is the outlet flow from the previous tank, and outlet flow from the previous tank and inlet flow for the next tank. So it's also the outlet flow. And to do that, we multiply this height. Well, we multiplied it by b, our constant, remember? Right, I think I circled it. Yeah, right here. So I just multiplied by b to get our outlet flow. Pretty simple. So now we have Q1. Well, now we're interested in, of course, height 2. And height 2, of course, now you see the pattern here. Height 2, we relate back to Q1 somehow. Well, height 2, Q1. Well, how do we relate to height and flow? Well, that was through our first order differential. Then moving forward, you kind of hopefully see the pattern here. We have Q2, and that's from the height of the second tank. Again, this is the outlet flow from the second tank. So that's why we can relate it, excuse me, with our B. And then now, lastly, we have height 3. Since we don't really care about this Q3 outlet going out of the tank, we're interested in the height of the last tank. So we're just saying arbitrarily we're going to stop at third tank here. So that is just, well, going off the previous flow, so Q2, and again, the first order. The first order transfer function. So now, if I write all of this out, let's see, somewhere here maybe. So let's use this, why not? Or brown. So we're interested in the height of 3, I believe, from the problem statement. So this is equal to, I'll write the constants out first. So we have Q2, which will be subbed in here. So hopefully you see the pattern ready. So we have K, our system gain, tau s plus 1. And then, so substituting Q2, we have H2 times B, so the height of tank 2. So we'll sub that out, but then I'll write it here for now, B. And then we have, I guess I can sub in the K's now. So remember K was 1 over B right here. So hopefully you saw that. Okay. And so I'll put it here for now. And then, so right now we're on Q2. So Q2 we multiplied by B and we substitute H2. Well, H2 is right here. H2 is this Q1, but first we'll have to get this expression first, this first order transfer function. So we write that again. Now we substitute Q1 again right here. Q1, and this was our height and our B, so we have another B. And then height 1, final substitution, height 1 is Q in, and then our transfer function. So Q in, and then our transfer function. So that's 1 over B, tau s plus 1. So we have this very long expression, but you realize it just simplifies down to, well, let's see, we have these cancel, and we have 1 over B on the top still, 1 over B. And then let's see, we have 1, 2, 3 tau s plus 1s. So we can cube that. And then we have our Q in. So now we just have one expression. And remember, we just multiplied across. So pretty simple, I would say, for every tank. So actually, this can actually, so this can be represented with a block diagram. You can do something like starting with Q in. Oops. So we have Q in. We have our system transfer function to get our height. Remember, we did our transfer function, so do 1 over B tau s plus 1. And then from the height of one tank to get the Q1 of the other. Did I do this correctly? Yeah, I'm pretty sure. We're multiplying. So then H1, the height of first tank, we multiply by B, get our first flow right here. Right now we are right here. So essentially I'm going something like, hopefully these arrows make sense. Q into H1, H1, H1 to Q1, Q1, Q1 to H2, H2, H2 to Q2, and so forth. Again, relating flow rates to heights. So we just multiply by b to get our outlet flow. And then this is another tau is plus 1. I'm sorry, transfer function. Hopefully, yeah, height 2. I'll bring that around. And height 2, what do we multiply by? B, get our second flow rate. I guess second outlet. I don't know. Technically third, but second outlet flow. No, it is second outlet flow. And then we multiply by our transfer function one more time. And now we have, well, our height. Or right here. Height of third tank. Again, noticing we have 3 of our expressions, just checking this. 3 of our transfer functions, 3 of our transfer functions, and then 2 b's. Remember, that's our constant we use to relate to outlet flow from our, to relate to height from our outlet flow. That's right here, 2 b's, and then of course we have our qn. Right there. So yeah, essentially it boils down to the same exact expression that we did already before. So yeah, this idea of block diagrams kind of helps paint the picture, or well, one visually, but also to see like how we're just essentially just doing an algebraic multiplication. We just multiply straight across. If for however many inputs and outputs, we just go through each box, and that's what we multiply by. So I believe that's everything we've done. So yeah, we did our simple tank first. Doing the Laplace domain after linearizing it from a Taylor series expansion. I showed you why we chose the initial steady state h bar as a point of expansion, the importance of that, and how that let us simplify our Laplace transform versus if we just did arbitrary value. And doing that allowed us to simplify all the way down to our first order transfer function right here. And after doing that, we did our series of tanks, which was pretty simple, relatively easy using algebraic multiplication and relating the expressions between the tanks. The key pretty much here was somehow relating our outlet. Ooh, that was eraser. Our outlet, I don't know, here, our outlet to our height of the previous tank. So remember our outlet flow, this whole thing here was our outlet flow. So if we want to relate it to the height, we use our b that we defined earlier. So yeah, pretty sure that's it. Hopefully got everything correct. Okay. I'll see you in the next part. I think we're going to be plotting this up and showing a graph of it. So yeah, thanks for watching.